Hello, welcome back to your physics teacher. And in today's lesson, we're going to be looking at Newton's first law, section 3.2 from Nelson textbook for Physics 11. The question number 2 reads, which has the most inertia, a truck, a desk, or a feather? Which has the least inertia, and how do we know? Before answering this question, let's try to quickly recall the definition of inertia. Inertia is the tendency of an object to resist a change in motion. This means that if we have an object that has a large mass, then this object with the large mass will also have a large inertia. Right? If you think back to a large object, it is much harder to get a big object to move that's heavy than a lighter object to move. So that's what we mean by resistant motion. So heavier objects are harder to get them to change their motion, whether that it is to get them to move or once they're moving to stop them. Imagine trying to stop a truck. It's not so easy. Oh, right away. So in the example I was trying to give you, it was in the question. So yes, a truck has a large mass. So once it is moving, it is really hard to get it to stop moving. Or the other case, if it's stationary, it is hard to get a truck moving by trying to push it. So we can rank our objects by mass, which is the same thing as ranking them by inertia. So when we are comparing a truck, a desk, or a feather, we know that the truck has the largest mass. Then we suspect that a desk will have a larger mass than a feather. So we can rank objects by mass, and it's the same thing as ranking objects by inertia, which is the tendency of an object to resist motion. So objects in motion tend to stay in motion. Recall Newton's first law, which is the study for this particular section. Let's take a look at the next question now. Question number 3 asks us, skater 1 has a mass of 45 kilograms and is at rest. Skater 2 has a mass of 50 kilograms and is moving slowly at a constant velocity of 3.2 meters per second east. Skater 3 has a mass of 75 kilograms and is moving quickly at a constant velocity of 9.6 meters per second east. Which skater experiences the greater net force? And they want us to explain our reasoning. As a quick recall, we know that the net force represents the sum of all the forces acting on an object. So in this case, we can represent it as F net. And again, we have the sum of all the forces F1 plus F2 plus F3 and so on. And we also know so far from Newton's first law that if an object has a net force of 0, then either the object is at rest or moving with constant velocity. So we're going to use the first law to help us look at these 3 skaters and see which one is experiencing the greater force. So let's list out the 3 skaters. And let's go back to the question and see what each of these skaters are doing. Now, skater 1 has a mass of 45 kilograms and is at rest. Skater 2 has a mass of 50 kilograms and is moving slowly at a constant velocity of 3.2 meters per second. So the key part here is going to be constant velocity. And the third skater has a mass of 75 kilograms and is moving quickly at a constant velocity of 9.6 meters per second. Another part here to take away is going to be the constant velocity portion. And notice that from Newton's first law, we concluded that the net force is equal to 0 if an object is either at rest or moving with constant velocity. So in each of these 3 cases, we have that the net force equals to 0 because they meet the criteria that we have just given out. So this means that in all 3 skaters that we have, they all experience no net force. This question here was trying to trick you by using words moving slowly or moving quickly. So it was trying to make your brain tricked by this question, or even changing the mass by making one object light or one object heavy. So when you're looking at this, you need to identify the net force, but we know that the net force equals 0 for object at rest or moving with constant velocity. Here, question number 6 says, many people buy a coffee or other hot beverage on their way to work. For safety, the cup usually has a lid and is placed in a cup holder. Using Newton's first law, explain why both of these precautions are necessary. Since they tell us explicitly to use Newton's first law, first let's try to recall what Newton's first law says. So Newton's first law says that an object in motion tends to stay in motion, or an object at rest stays at rest, unless there's an external unbalanced force acting on it. So if we were just to have this cup of coffee by itself, nothing will be wrong with it. So we wouldn't need a cup holder or we wouldn't need a lid. But if this object happens to be stationary and is, let's say, on the windshield of your car, then when you accelerate, let's say you go towards the right, then the cup wants to remain stationary. So the car goes to the right, but then the cup wants to stay stationary, so which is the reason why it spills over downwards. The other case is you already are moving with uniform motion, so in other words, you're cruising along, and suddenly you come to a stop because you see an object up ahead, or possibly a red light. So you want to apply the brakes. But since the cup already thinks that it's moving with uniform motion, it wants to continue moving with that particular motion, which you could think it's moving to the right. And when the car brakes, so in other words slows down, then the cup, still thinking it wants to remain in motion, will then go to the right and hit the windshield, so make another mess. We can avoid all of this by putting the cup in a cup holder. And this will prevent the cup from falling forward or backwards depending on the change of motion. But then we have to consider one more case. Why do we have a lid? So with the lid, it helps to prevent the splashing of the liquid inside. So in the case where you're cruising along and then suddenly come to a stop, so let's say you're cruising along to the right and suddenly come to a stop, then that means that the water wants to keep on staying, not the water, the coffee will then splash outwards on the left. Or if you already are at rest and then you speed up, then the coffee wants to remain at rest, so it will splash the other direction. So in both cases, to prevent the splashing, you need to have a lid. And ideally, you have both of these scenarios happening for the cup holder and the lid. So this means that if you want to have your coffee in the morning, you should be either completely stopped at a red light or enjoy your cruise. Because when you're cruising along, then you can enjoy the coffee because it's moving with the same speed as the car. But just keep in mind that if there's a red light, sometimes there's crazy drivers, so you want to watch out behind you and see that they don't hit you. So just focus on the road, okay? Here we have question number 7. So it tells us figure 10 shows a string tied to a spike at one end and a puck at the other. The puck is moving around in a circle on the ice. Describe what the puck will do if the string is suddenly cut at the red line. Explain your reasoning using a diagram. Alright, so first let's just redraw this diagram. Alright, so here we have the puck tied to a string attached to a spike, and they're showing us that the puck, its initial intention is to be moving around in a circular type motion. But the question is, what would happen if suddenly we were to cut the string along the red line in the diagram? So here we're going to cut the string. In this case, we need to remember Newton's first law. So at the moment we cut the string, what we're really doing is we're cutting away the tension force. And recall that the tension force always pulls away from the object. So if we're considering the puck as our main object, the tension force will be to the right. But if we were to cut the string, then there is no more tension force. So if there's no more tension force, then there is no unbalanced external force on the puck. And because there is no longer an unbalanced external force, then the puck will remain in motion from the moment which it was cut from the spike. So at the very moment that you cut the string, the velocity of the puck is going to be tangential to the circle. In other words, perpendicular to it at that very instant in time. So the velocity is perpendicular at that specific moment in time. So once we cut the string, an object in motion will want to keep in motion, and because the force was moving it to the right and no longer we have that force, then the puck will continue moving along the direction of velocity along a straight line. So instead of going around the circle, it will move along a straight line due to the law of inertia, because there is no longer an unbalanced external force. So it will keep on moving with the velocity it had the moment it was cut. Let's look at question number 8 now. Question number 8 says, use Newton's first law to explain why the normal force must be equal in magnitude to the force of gravity for an object to remain at rest on a horizontal surface when no other forces are acting on the object. Let's start off by looking at a system diagram merged with free body diagram. Okay, so here we have a sun bear teddy bear. And these sun bears, they're really cute because they look like they have a gold chain across their chest. You might want to Google that, they're really cute. And here we have this sun bear at rest on top of a surface. So the two forces that are going to be acting on it are going to be the force of gravity, which will be pointing downwards. And in this case, because there's an interaction with the surface, we're going to have the normal force, which acts perpendicular to the surface, which will be pointing up. Now in this case, we have that the object is stationary. So we know that if an object is at rest or stationary, that the net force acting on it has to be 0. And they told us that in the question there could be no other forces acting on this object. So this means that when these two forces are added together, they need to add up to 0. And the only way for this to be true is if the normal force equals to the negative force of gravity. So what this means is that the normal force is in the opposite direction of the force of gravity. But furthermore, that the magnitudes have to be equal. So these two forces are equal in magnitude and opposite in direction. Again, this is not always true. There are cases where the normal force could be smaller or higher than the force of gravity. So this is only true when there are no other forces acting on the object along the vertical component. Let's take a look at question number 9 now. Question number 9 asks us, you are inside a car moving fast along a sharp turn in the road. Use Newton's first law to describe what happens to you as you safely make it around the curve. So you are inside of a car moving fast along a sharp turn in the road. Okay. Here we have our car, and inside the car, you're moving fast along a sharp turn. So let's draw the path. Now, what's going to be happening to you according to Newton's first law? Well, you just have to think back to when you're actually inside the car and someone's making a turn. What do you actually feel? So whenever you're making a left turn, you feel as if you're being pushed to the right. This means that in this case, we use the word pushed. And if you recall our definition of force, a force is either a push or a pull. So you might suspect that this is actually a force. So we can call this F. Now, in the previous lesson, we identified all the forces, not all, but we identified most of the forces that we'll be studying. And it turns out that this force that you think you feel is not a real force. So it's not one that we can identify. We're going to call this force a fake force or fictitious force. So it turns out that it's not actually a force. And this mainly occurs whenever you have motion happening in circular motion, so which means whether you're turning to the left or to the right while making a curve. Now let's see what is actually really happening by using Newton's first law. Recall that an object in motion stays in motion. So if we were to consider at every single moment in time during the turn, your body wants to continue moving forward in the direction of velocity. But since you're trying to steer to the left, there has to be another force that's acting on the car that's making it go to the left at this very moment in time. And that's due to the interaction between the tires and the surface, which we can call the frictional force, FF. This means that technically your body wants to continue moving a straight line due to Newton's first law, but the frictional force is pulling it towards the left, the car that is. So your body actually wants to continue moving in the direction of velocity, but due to the car moving to the left, there's a fight between the two situations at hand. This means you continue moving to the straight line, but it feels like you've been pushed to the right due to the friction force pulling towards the center of the circle. So again, to make it clear, the frictional force is pulling the car, but your body's inertia wants to move forward in the direction of velocity. Thus, this actually feels like there is a force pushing you to the right. This also works if you were to be turning to the right instead. You feel like you're being pushed to the left, and that's just due to the inertia at hand, in this case, due to Newton's first law. For question number 10, they want us to use Newton's first law to explain why you should slow down when going around the curve on an icy highway. Okay, so let's consider back our car again. And here we want to go around in a small circular curve. But what do we know from before? At every single moment in time along this circle, tangentially, you're going to have your velocity. And what fights the inertia of going forward is the frictional force pulling towards the center of the circle. So in this case, if we think about the ice on the highway, then it's going to be more slippery. So in ice surfaces, the frictional force tends to decrease in value. So you can imagine that in ice, your frictional force decreases in magnitude. So this is going to make it really hard for the inertia to be fought of the car wanting to keep moving forward. So in this case, this is why you should try to slow down when going around a curve on an icy highway, because your body will want to keep moving forward along with the car, and the frictional force is not strong enough to make it keep going around the circular motion. So you're just going to keep on going forward. And possibly hitting something. Question 12. While on the bus, you throw an apple straight up into the air. What would happen if the bus A moves at a constant velocity, B slows down, and they want us to explain our reasoning using diagrams. Okay, so here we have a person sitting on the bus, and they have an apple held up straight up in front of them. And they want us to explore what will happen if the bus moves at a constant velocity. So this situation is quite difficult to imagine because you have to imagine it from two different points of view. So from the point of view of you as the person riding the bus, it appears that the apple just goes up and comes back down into your hand. But the motion is completely different if you imagine from an observer looking at the bus go by, it appears that the apple goes up along an arc and comes back down. So in this case, in the first one, whenever you're moving with a constant velocity, if you're observing from an outside observer, then it looks like the path of the apple is going to be an arc, which reminds you of projectile motion. And what happens in projectile motion, assuming that you're moving with constant velocity, because that's what they told us, it moves at constant velocity. So at every point, the velocity of you in the seat is equal to the velocity of the bus. And this also holds true for the apple at any point along its path. So the velocity of the bus will be the same thing horizontally for the apple while you're throwing it in the air. So if you think back to projectile motion, only the vertical component of the apple's velocity would change as it goes up and comes back down. So as the apple rises, the vertical component will be getting smaller, but the horizontal stayed constant. And as it comes back down, the vertical component gets larger, horizontal stays constant. And this means that because the horizontal component did not change, then the same horizontal distance is covered by the apple as it is by you that was riding on the bus. This is the reason why if you were to throw an object up into the air, it falls back down into your hand. Because horizontally, you're moving with constant velocity and thus travel the same displacement horizontally. Let's look at the second scenario. If you're to throw the apple straight up into the air, but then the bus starts to slow down. So in this case, from the point of view of the rider on the bus, as you throw the apple upwards, and then the bus slows down, then the apple will appear that it fell in front of you. So again, whenever you throw the apple upwards, but then the bus slows down, from the rider's point of view, it appears that the apple falls and hits the ground in front of them. But now let's see what happens from the point of view of an observer watching this happen. So as we saw before, whenever you throw the apple upwards, then it's going to start to follow a parabolic motion and it falls down. And in this case, it fell in front of the rider because as we saw before, when you threw the apple upwards, it maintained the velocity of the bus initially. But because now the rider is no longer moving with this velocity, they're moving at a slower rate because they were slowing down. So the velocity of the person is going to be less than the velocity of the bus initially. So horizontally, this means that the apple will cover a larger horizontal distance than the person riding on the bus. Because again, in projectile motion, the horizontal component of the velocity is not going to be changing. So this means that it's going to maintain its motion horizontally, thus being able to cover a further distance than the bus, because the person on the bus slowed down, so horizontally they cover less distance. And this is going to be our last question for this particular video. I hope that you stayed with me and you're finding it useful, please hit like and subscribe, and that way you can watch more videos. And please show your support by putting a comment, and I'll appreciate your help to help my channel grow. And question 13, it says determine the indicated forces on each free body diagram shown in the figure 12. So in part A, they have that a statue is at rest on a shelf. If the statue is at rest on the shelf, what do we know from Newton's first law? That the net force acting on it has to be 0. This means that the horizontal components add up to 0, and then the vertical components also add up to 0 separately. So let's consider the vertical components. Notice that the missing force is F2, but we have that there's a force of 32 newtons downwards. So in order to balance this out, there needs to be another force of 32 newtons upwards. That way, when you add them up, they give you 0. Likewise, we look at the horizontal parts and notice that there's 17 newton to the right. In order to balance out, we need a 17 newton force to the left. That was pretty straightforward. I don't think you needed much help in this one, but just to be complete in my video, right? And for part B, they say that a sled is pulled right at a constant velocity. So again, here the key part is constant velocity, which tells us from Newton's first law that the net force acting on it should be 0. So like we did before, we're going to consider the vertical components. And there's a 54 newton upwards. So in order to balance this, we need a 54 newton down force. Then we take a look at the horizontal components, and we have an 86 newton force to the left. So on the right, we need a combined 86 newtons as well. But there's a 60 newton, so the leftover is going to be a 26 newton force to the right. So it's kind of like a puzzle. Not the most complex puzzle. Sudoku is still probably harder than this. But anyways, it does get harder, so please hit like. That way you can stay tuned to watch the harder videos for Newton's second and third law. Until next time.